Well, no, the idea is like, this is the axis that goes from its closed universe to its an open universe.
Oh, okay.
Yeah.
Yes.
So if you go far enough that way, do you come back from behind? That would be a closed universe. Or is it flat, or is it open, which is very hard to explain, like physically, what would that mean? But it changes the way that the expansion rate and the gravity would counteract each other, basically. And so you can theoretically invent all kinds of universes.
Today we had the pleasure of talking with Professor Sarah Martell. She's a professor at UNSW and also a observational astrophysicist. We had the pleasure of sitting with her in an observational room and look at how she does her research. We also talked about concepts such as human civilization and how it's going to evolve. We had a look at how the evolution of a universe might affect how this civilization looks at the science that we have discovered today. So this was a very special chat with Professor Sarah Martell. Let's begin. Professor Sarah Martell, thank you for coming on my channel today. It's really a pleasure to have you here.
Oh, it's always good fun to talk about space, right?
Before I start, I want to ask you, what exactly is astrophysics and what do astrophysicists do?
Ooh, all right. So there are a lot of different ways to answer the question, sort of what is out there. And so all of those, I would say, is astrophysics. Every way that you can get into the question of how did the Earth get here, or why is life on Earth the way it is, or even just sort of why are galaxies the shapes that they are. There's a lot of why questions and how questions, and all of those work as astrophysics.
So I think everything that sparks curiosity is basically astrophysics.
I mean, I would argue that, yes.
So you have done a lot of research in the history of our galaxy, the evolution of the galaxy, and how it's going to evolve over time. So would you like to shed some light on that?
Ooh, okay. So our galaxy is about 12 billion years old.
Oh, okay.
And the whole universe is 13 and a half or something, 13.8. And so our galaxy did not start straight away at the very beginning of the universe. It took a little while to get going. But it is very old, right? So the oldest stars that we know are sort of 12, 13 billion years old. But it's currently still forming stars, right? So it's been actively doing things, changing and growing that whole time.
Wait, so how does a galaxy grow?
Okay, so mostly by eating their neighbors. It's not a very nice environment. The whole sort of the whole idea of large scale structure in the universe is that gravity's in charge of everything, right? And so when you start forming little proto-galaxies in the very early universe, they'll see each other through gravity, and they'll be attracted to each other, and they'll come together and get bigger. And as you do that, what you end up building is like a small number of big galaxies that are eating all their neighbors.
Oh, okay.
And so a galaxy as big as the Milky Way has gotten that size by being the combination of a bunch of smaller pieces. And we are still in the process of eating our neighbors right now. That's actually what we're observing here tonight, is some previous galaxies that are in the process of being consumed by the Milky Way.
Oh, so like the one that we know about, maybe the audience knows about that as well, is the merger of Andromeda and the Milky Way galaxy.
Oh, so that hasn't happened yet.
So yeah, I think, and
that's 5 billion years away.
Really?
Yeah.
That far away?
Oh yeah.
Oh, and they talk about it like it's coming.
Oh, it's definitely coming. I mean, Andromeda is coming straight for us. We can definitely calculate forward what are the paths of the galaxies, and they're definitely going to run into each other in about 5 billion years.
So what will happen when these galaxies merge, and like these are two big scale galaxies?
Yeah, so surprisingly little will, on the scale of stars, will happen. Most of a galaxy is empty space, right? And the space between stars is much bigger than the stars themselves. So if you run two galaxies through each other, most of the stars just go right past each other and don't notice. The gas will care. The gas will collide, and often when galaxies interact like this, you touch off a whole lot of star formation. So you have a whole burst of new stars that form at the place where the gas from the two galaxies ran into each other and sort of got squished down and made more dense.
Right.
And the black holes will eventually merge. So being large galaxies, the Milky Way and Andromeda both have a supermassive black hole at their center. And so as the galaxies continue to interact, those two will get stuck and then eventually spiral in, and then make a bigger supermassive black hole.
Wow.
Yeah.
So when we talk about that supermassive black hole that's in the center of our galaxy, that's not responsible for the stability of the whole galaxy.
No, it's really not most of the mass of the galaxy. It's big. It's the single most massive thing in the galaxy, right? But the dark matter halo of the Milky Way is actually much more important than the supermassive black hole.
So, what is dark matter?
Oh, we don't know. That's a great question. No, I wish we did. There are thoughts that it might be a special kind of particle. There are thoughts that it might be a particular kind of neutrino. It is tricky because all the evidence we have for the existence of dark matter is that there's more gravity than we think there ought to be from how much bright stuff there is. So you can look at how many stars are in a galaxy, you can convert that to how much mass should be there, and the orbits of the stars act like there's more mass than that. And so, the idea of dark matter is, okay, so there's something there we can't see, but that it exerts gravity. But then the particle physicists have to try to make that an actual functional thing. How do you make a particle that doesn't interact with the electromagnetic force, that doesn't interact with the weak force and strong force? It's just gravity. Nothing else that we know about does that. There's also a possibility that there isn't actually an extra particle or an extra source of gravity, but in fact that gravity is not as strong on very large distances as we thought it was. That we have this idea that the force of gravity goes as 1 over r squared as you get farther away. The effect of it goes down, very quickly.
Right.
But it might actually be a little faster than that as you get really far away. This is an idea called modified Newtonian dynamics. It says maybe gravity just isn't as strong at really large distances. The problem with it is it's extremely hard to test because you need very precise measurements of how the accelerations of objects, right, the force of gravity at very large distances, and it's just really hard to be that precise.
Why couldn't they just be like mini black holes that are just swooshing past our galaxy and they are making that effect? Because we can't observe black holes in easily, at least we can't, and we won't be able to observe those small black holes. So why couldn't it just be that?
So we've thought about that. So it's funny. The particle physicists gave their idea an acronym called WIMPs, so weakly interacting massive particles, and the astrophysicists gave this little black hole theory an idea called MACHOs, massive compact halo objects. We had WIMPs and MACHOs, which is a little ridiculous as a science fight. So the idea was, what if there are just black holes out there, and as long as they don't interact with any gas, maybe we wouldn't notice them, right? The thing the astrophysicists realized was you would be able to see them through gravitational lensing.
Right.
Yes.
So can you break that down for us?
What is
gravitational lensing?
So gravitational lensing is a space-time thing. It's a general relativity consequence of the fact that gravity actually bends space-time. And so if you have sufficiently strong gravity, the path that light takes is actually not a straight line. It follows the shape of the space-time. And so if you have something sufficiently massive, or if your alignment is just perfect, your light, instead of sort of following straight lines, will be curved a little bit. And so if you're looking at an object behind something massive, it might look brighter than it should. And particularly if your object is moving through your line of sight, then it would get brighter and then get fainter again. And this is an effect called microlensing. And so we've done a lot of studies to look for microlensing. And it turns out we don't have any evidence for massive compact halo objects. Which is unfortunate, because it was a cool idea and it had a great name. But MACHOs, as far as we can tell, don't exist.
Right. So when you look at the universe, you see a lot of symmetry in it. For example, even the atoms in our body, they have a lot of space between the nucleus and the electrons that are going around it. And like you said, there is a lot of space in our galaxy. It's huge, but mostly it's space. So just like that, I was wondering. So there's a sun at the center of every solar system. There's a star, which is it's responsible for the stability of that solar system. Then at the center of every galaxy, there is a black hole.
Probably.
Why do you say that?
Well, I mean, all of the massive ones where we've looked, there's a supermassive black hole. And so we think that there's probably something really fundamental about the way that you make a system as big as a galaxy. But what if you had a really small galaxy? Like, is there a lower limit of, if you have a small enough galaxy, whatever this crucial thing is that makes a supermassive black hole didn't happen? And where exactly is that line? And we don't really know.
But would that even be called a galaxy? I mean, that's just a cluster of stars that have come together.
That is an excellent question that we argue about a lot.
Mm-hmm.
What is the definition of galaxy? In fact, there was a very well-known researcher who did an internet poll 5 or 10 years ago to prove the point that people don't agree on how you define this. At the moment, I think what we've settled on is that galaxies have dark matter and star clusters don't.
Oh, okay.
And so that means there are lots of things that are galaxies that don't have supermassive black holes because they're very small galaxies. But then also it means that we need to go look at a lot of star clusters that are fairly large and see if they have black holes, because they might actually be galaxies. And so it's this very fuzzy boundary line.
It's like saying, is Pluto a planet?
Yes.
Yeah,
you have to make a definition that makes sense.
Right. So after this, I want to dive into science fiction with you.
I love science fiction.
So I'll tell you my story first.
Go for it.
So I think I was 10 or 11 years old when there was a space workshop happening in our school, and I took part in it. And for the first time I saw Saturn. And when you see Saturn through a telescope, you see its rings, and
it just doesn't seem real.
It doesn't.
Yeah.
And I mean, these things just humble you out a lot. They show you how massive the actual world is and how tiny you are compared to everything.
Yes, I agree.
So after that, I think I watched Cosmos hosted by Neil deGrasse Tyson, and I think most of our audience here would be fanboys or fangirls of that series.
Oh, sure. Yeah.
But after that, I watched a movie, Interstellar, and I think that really opened up my brain. So there are a lot of science fiction ideas discovered in that movie, and I think most of them are true if we look at are theoretically true by Einstein's equations, such as wormholes and time dilation, and then going inside a black hole. So I think I would like to ask you first of all what time dilation is.
Okay, so time dilation is an effect of general relativity. It says when there's a very strong gravitational force or a very strong acceleration, your personal experience of time is slower than other people's.
Right.
Which is weird. And the amount of difference between your experience and other people's experience depends on how fast you're going. So as long as this is that regimes thing again, as long as you're slow compared to the speed of light, there's no real difference, right? As long as gravity is fairly normal, there's no real difference. But in Interstellar, they have this system where there's a black hole with a planet orbiting it. And I really like how they set it up, because they left one of the astronauts in orbit.
Yep.
Where the gravitational field is weaker. And so his personal time was more normal. But the people who went closer to the black hole, experiencing the stronger gravitational field, experienced more time dilation. And so their personal time was slower. And they didn't, the amount of time they experienced was not all that long.
Right.
This was the planet with the giant wave, and just barely escaped, and it feels very fast and very rushed because they just barely made it out of there. And they get back to their other astronaut, and it's been years. And he didn't know what they were doing. And this is sort of a very dramatic illustration of the effect of time dilation. You'd need some pretty significant gravity to cause that big of an effect.
Right.
I mean, we can measure this for real with satellites orbiting the Earth.
Is it?
Yeah, they're 20 kilometers up or something.
Right.
But that's enough of a difference in the gravitational field between the surface and where they are that a couple milliseconds. And so if you want to use a GPS satellite correctly, you have to actually account for that.
Also, you have to fix the time in the satellites that are orbiting.
Yeah, because their clocks are a little bit slower. Faster.
I think 7,000 nanoseconds.
Yes, yeah.
In Interstellar, they show a possibility of what could happen if you fall into a black hole. And I think what they discover is that time becomes three-dimensional in a way. So you can go back, you can go forward, and you can play with time, and the whole timeline is basically in front of you.
Well, that was a beautiful visualization. I really enjoyed watching that. And just the thought of, almost like a library of your life.
Yeah.
which is just, they did such a nice job of being able to see like how the guy was experiencing, being able to, you know, touch all these different points in time, because our normal experience of time, it only goes one way, right? And so it would be pretty overwhelming as a person to have access to all of those things.
Right.
The thing about black holes is that we have absolutely no idea what would happen. And if you were to go and find out, you have no way of communicating that information back out.
Because it can never leave the black hole.
Yep.
So another thing that interests me is the quantum field theory. So I think it basically states that everything is a field, and everything that we observe is because of those fields and merging of those fields. So I was thinking, could the consciousness, I don't know if you want to answer this or get into this, but it's completely up to you. I was just wondering if this consciousness can be universal as well.
Ooh.
Like, is there a field, could there be a field for consciousness as well?
So obviously people have individuality and sort of self-direction and things that you might think are part of consciousness. The ability to look at something and decide what you want.
Right.
But plants do that. Animals do that. So do we want to say that there's something special about people? And or is it something that's intrinsic to life that you know, has this sort of will as opposed to just sort of an autonomous carrying on?
True.
I don't know. I don't actually know where I sit on that. And then if you want to extend to questions of astrobiology, we don't even know what life elsewhere in the universe might be like. It could be microscopic organisms, it could be, you know, aliens like from TV shows, it could be lots of things. And it may function very differently to how we do.
When we do talk about aliens, let's say that there is species in Alpha Centauri, maybe, let's assume, and they aren't intelligent, they are maybe like animals on Earth. So will we be able to find them because they aren't emitting any light, or are there ways currently in science to find that kind of life?
So the idea of biosignatures is that when things are alive, they affect the environment, and if they affect the environment enough that it shows up in the atmosphere, maybe we could tell. There are particular compounds in the atmosphere that on the Earth are only there because life keeps putting them.
Right.
Oxygen is a particular example of this. That if you put free oxygen in the atmosphere, it'll bind to other things. It makes CO2, it'll make water, it'll make other stuff. And so if you see free oxygen in the atmosphere, our conclusion from looking at how the Earth's atmosphere works is that something put it there. So if you look at other planets, and you look at what's in their atmospheres, and you see free oxygen, then the reflex is to go, oh, it's just like Earth, right. Therefore, there must be something that lives there and, you know, respirates and produces oxygen. But, of course, there's a big assumption at the beginning of that, which is it works just like Earth does.
Right.
Life from elsewhere could be so different to us.
Right.
And the things we think of as making people special could be just one of very, very many ways of being interesting beings that relate to each other. And chemistry was the same everywhere. This is the cosmological principle again. But without knowing the full assay of what's in that atmosphere, you can't really predict what the reaction networks are going to be.
Right. So
but the point is, you don't need any kind of techno-signature to necessarily to know about life. It could just be the effect that it has on the atmosphere because it breathes.
True. Science, like, it is hugely driven through wars, I think, science and technology. For example, in World War I, we had a lot of innovation in neurology. When we saw that a particular part of brain, when it's damaged, it's not affecting the whole body, but certain parts of our body. For example, someone lost their vision, and etc. And then in World War II, we had a lot of innovation in chemistry, the atomic bombs and everything. And then in the space, in the Cold War, there was innovation in space technology and everything. The first man went to moon. But after that, we have seen a decline. I mean, in ways like the government isn't really funding science and technology. It has become more private. For example, Elon Musk and Jeff Bezos. So, what do you think science fiction, movies or books, what part does it play in shaping our society and culture?
I have so many feelings about this. I think the example of the Cold War is a great one, because it's such, like, the motivations are so clear.
Right.
It was, from both sides, it was, we're going to prove that our philosophy and our economic system is superior by doing this really difficult thing before the other guys can. That had nothing to do with learning about how space works or making new materials or all of the computer development that happens, where, you know, the Apollo missions, the computational power on board was like a pocket calculator these days. But they could take it all the way to the moon, right? Because it was very, very carefully put together, programmed by, you know, experts who knew how to make the very most out of a very limited system. Those people would have done amazing things with any motivation, right? I'm thinking of, you know, Margaret Hamilton, who led the programming for the Apollo missions, or, you know, all of the people at the Jet Propulsion Lab who did all the materials work to make things that can actually get through the atmosphere, spend weeks in the vacuum of space, come back through the atmosphere and, like, not be broken. Those people have an amazing amount of talent, amount of knowledge and motivation, and if we let those people do new things, they would do so many great new things. Yeah, that's how I feel.
Yeah, I think you're right, because humanity as a species, it has always been driven by curiosity, and if given the right resources and the right funding, I think we can achieve a lot of goals.
Yeah, and I'd love to see some success in that paradigm, right? I think actually the Indian space program is a good example of this.
Yeah, I think ISRO is doing really well, and
because they've recently been putting missions out, and not to, like, stick it to Russia, not to prove it on the political stage, but just because they want to do it.
Yeah,
it's been really exciting to see.
Yeah, it's mostly driven by, like, curiosity and the wish to know and to progress in technology and science.
Yeah, exactly.
Yeah, they're doing amazing. Would you like to talk about your research and everything, the observations that you're making?
Yeah, I'd be delighted to. So we are in the remote observing room at the University of New South Wales for the Anglo-Australian Telescope, which is a 4-meter optical telescope that is located at Siding Spring Observatory. It has a variety of instruments for a bunch of different science cases. And the one that we're using tonight is a spectrograph called AE Omega. So a spectrograph takes the light from the object you're interested in and it splits it up basically through a prism.
Just before you continue,
yes,
what is the spectrum? Like, what is it being used for?
Oh, yeah. So with stars, when you take the light and you split it up into a spectrum, you can measure quite a lot of information about the star. So you can work out redshift. So if you look at whether the features in the spectrum, we'll get to the spectral features in a second, but if they're at the wavelengths they should be at, then you know that the star is not moving toward you or away from you. But if the star is moving away, for example, then those will be redshifted.
Right.
They'll be at redder wavelengths than they're supposed to be. And so we can use the strengths of those lines to work out sort of what's the temperature in the atmosphere of the star, how much of that element is there, and that kind of stuff. And so that's part of our research. So partly we want to understand, do these stars belong to these streams? And so we need to know their radial velocities in order to work out the orbits around the galaxy, figure out if they belong to the stream. But we also want to know what are the stars made of, because if the stream was originally a galaxy that's being eaten by the Milky Way, then it should have some consistency in what the stars are made of. Right. They would have all evolved chemically in the same environment, and so they should have similarities in their big abundance pattern across carbon and magnesium and iron and titanium and lots of other things. And so we can work that out from the spectra, from looking at how strong and where in wavelength those features are.
Oh, well, mind blown. Yeah, it's amazing.
It's good stuff.
So this is a personal question, and you know, when you think about the universe, it's much bigger than what we can see. Like the observable universe is much smaller. We don't know the exact size, but maybe.
But there is a limit because the travel time of light is,
right.
The speed of light times the age of the universe, and that's all we can see. Yeah.
And that's because of something known as dark energy?
Well, I mean, that's always going to be true with or without dark energy.
How?
So the universe has an age, right? It's 13.8 billion years old, as far as we can tell. And so the farthest away light source we could possibly see is 13.8 billion light years away.
Right.
Right? And so if there's something past that, we don't know.
But why, if there was no dark energy, why would this expansion accelerate? And also, like, wouldn't the expansion actually de-accelerate because of the gravity that's inside the universe?
So that we don't know. There are several different models for this. And basically you have these multiple factors that matter, right? So you've got your expanding universe that we just observe is happening.
Right.
For reasons. And so you've got your speed of expansion. You've got the amount of mass in the universe, and that'll provide a deceleration, right? But and then you've got what's called the underlying geometry of the universe, which is
space-time.
No, it's hard to explain. It's a mathematical thing more than a physical thing.
Are you like trying to put space in a 3-dimensional?
The idea is like this is the axis that goes from its closed universe to its an open universe.
Oh, okay.
Yeah.
Yes.
So if you go far enough that way, do you come back from behind? That would be a closed universe. Or is it flat, or is it open? Which is very hard to explain, like physically, what would that mean? But it changes the way that the expansion rate and the gravity would counteract each other, basically. And so you can theoretically invent all kinds of universes. You can have universes with no material in them, and then they just expand forever. And you can have universes that have exactly the right amount of mass that it will take them infinitely long to decelerate to zero. And so they will just expand forever. And eventually, after infinity time, they will stop, but it will take infinity time to get there because they have exactly the right amount of mass. Or you can have universes that are above that critical density, that have enough mass that they can actually recollapse. And theoretically, all of these things are possible. And so understanding the real universe means you have to make enough measurements of what is actually happening that you could tell which of those scenarios we're really in. You have to find enough measurable things that would be different between those different possibilities to try to figure out which one of those universes describes our actual universe. And so in the process of trying to figure that out is when people realize that actually we're accelerating faster than we used to be, which is totally unexpected.
Right.
Mathematically, you can do it. And the original formulation that Einstein did actually had a term for it called the cosmological constant. Right. That he was just like, you can add a constant here, and it'll change the way that the universe evolves. But didn't have a good physical intuition for what that might mean. And so when people went to measure very precisely how fast is the universe expanding, they found that it's speeding up.
Right.
We don't have any idea what would make that happen, so it became dark something else, right? Because we don't know what it is, right? So like dark matter, it shows up as gravity. There's an effect in gravity that we see, but we don't know what it is. And so this effect in the expansion rate became dark energy, because we don't know what it is, but it seems to be happening. Yes. And so there are plenty of people working on, and this is sort of a field theory question, sort of, is there something fundamental about space that as it gets emptier, it pushes itself out faster? As far as I know, there are quite a lot of different mathematical ways to explain this, but it's not obvious what the physical meaning of, what is dark energy, right? There's not an explanation that we can just sort of say, this is it. We could say, it looks like it's happening, and we're trying to figure out why that is, but we don't know.
As the space is expanding, even our bodies are expanding with it, but we cannot see that because of relatively viewing the whole world is expanding with us.
This is again one of those scale regime kind of questions. If you look at galaxies that are far apart from each other,
Right.
they're moving away from each other because, at a certain rate, because of the expansion of the universe. And they also have their own velocities relative to space-time, which makes this a little bit harder to pin down, because we're not just looking at things that are being dragged along by space-time, but they have their own individual actions, right?
True.
Within a galaxy, though, the gravity at the moment, given the current expansion rate of space-time, the gravity is stronger. And so the galaxy itself is not expanding because of the expansion of the universe.
Okay.
Right? But as we go forward in time, if this dark energy thing is real and the acceleration of the universe is happening and the expansion rate is going up and up and up, it will come to a point where it's not just very, very distant things where we can see the effect, but it'll be smaller scales as well.
Also, only the Milky Way and that cluster of galaxies, like the Andromeda and stuff, only that much of the universe will be visible. Is that it?
Well, what I mean is, you would start noticing that the relative motions of Milky Way and Andromeda would be affected by this expansion rate if it got high enough. Right now, it's not high enough.
Right.
And the mutual gravity of them is making them come together. And I suppose if you carried this far enough forward, the solar system would be expanded out as well by space-time. But you would need really a lot of expansion in order for that to be true.
Right.
That is not the current situation.
We are far away from that.
Yes.
But considering a situation in which this is happening, for example, let's take maybe 20 billion or so years after today, let's just assume, because at that time the universe will be much more different, obviously,
for a lot of reasons.
For a lot of reasons. And so the human species, or whatever species is there at the time, they wouldn't regard our books, our concepts as plausible, because the universe has changed dramatically and the things we were able to see now won't be visible to them then.
That's
So
an interesting thought.
what I want to ask is, for us now, we have a lot of scriptures from past as well, which we have just regarded as myths. So why don't we try to delve into them and try to think that they might be trying to tell us something that really was there at the time, and it has maybe it is gone basically from our side, and we cannot experience it anymore.
Well, it's an interesting question, actually, because if you go far enough into the future, you mentioned something about things moving outside of our light horizon. In that case, or in a far enough future universe where basically we've run out of material to make new stars out of, we might derive very different rules for what's interesting in space and for what's happening out there. We might not come up with any theories at all about massive stars, because there wouldn't be any. And all we'd have are like white dwarfs and remnants of small stuff.
Wait, why do you say this?
Well, so at the moment, the Milky Way is making stars, and it uses up gas to do that.
Right.
And there's only so much gas around. So after a long enough time, you'll have converted all your gas into stars, and it stays there, right? A star like the sun will eventually form a white dwarf, and it will just continue to be for the rest of the universe. And you won't get that material back, and you can't make new stars out of it. And so after a long enough time, the galaxy will be a very dim place. It won't be making new stars, it won't be making big stars. All we'll have are these sort of faint remnant things happening.
Right.
And so if you were to look at that universe, you might come up with very different expectations of how does star formation work, and why are those the things that exist in the universe, than what we come up with now, where we see stars forming fresh. I think there's something definitely interesting to be explored there, and what physics would you try to explain if you were in a universe that looked very different than the one we're in? But I think that's very different to cultural shifts over a few thousand years.
Right.
Because I think we're substantially experiencing the same world, but we're interpreting it, in ways that are based on our cultural experiences, and I do think there's a lot of really interesting and valuable stuff in the way that people wrote about the way the world works.
Right.
In previous times. I think that the curiosity and the wanting to make meaning and the wanting to work out what are the rules is such a universal thing. And I think that we find the same essential things no matter where we're starting from, because we're looking at the same world. We find the same rules. We might express them in different language or with different metaphors, but we're getting at the same underlying reality.
True. And just to put it out there, because I like to read a lot of like Hindu myths and everything. So what I think is, they, like the ancient scripts, they try to like picture everything, even the atoms and even the sun. They try to give a human kind of view to it.
Okay.
And just to put it out there, there are stories in Hindu scriptures which point out a person being at several places at a time, and I think something like this is possible in quantum physics.
Several places at the same time?
Like a particular atom having a wave function.
Oh, yeah.
And like it being like, it has a 50% chance of being this side of the wall and a 50% chance of being that side of the wall.
So there's a couple different things there that they're all very weird, right, about quantum mechanics. So one of them is, if you have a single object, you don't know exactly where it is, right? It has a probability distribution of where it is. So if you're looking at an atom, it's most likely here, but it might be a little bit over there. And so there are a couple different ways to think about this. And one of them is that it really is a little bit in a lot of places at the same time. And one of them is that it only is in one place, but if we were to go and measure a bunch of times, we would find it most of the time it's in here, but sometimes it's over there. And those are very different interpretations of what's really going on. Mathematically, they're the exact same.
Okay.
But what does it mean? Is it really in one place? Is it really a distribution?
Who knows?
People have a wavelength. Every object has what's called a de Broglie wavelength that has to do with your mass. And so the probability distribution of where a person is very narrow. It's pretty clear that we're right here and not over there.
Right.
But there's a very small non-zero possibility that with small particles, that wavelength is more observable compared to the size of the thing.
Right.
And so when we look at, where exactly is this electron? Somewhere in there.
Somewhere.
Yeah. Yes. The other thing you seem to be talking about is the idea of entanglements.
Yes, quantum entanglement.
Yes, which is also super weird. If you have two particles that for some reason affect each other, so like if you have two electrons in an orbit in a hydrogen atom, so you get your H minus ion. If they're both in the same ground state, one of them will have a spin up and one of them will have a spin down. And this is a quantum mechanics rule.
Right.
That they can't have the same spin and the same energy level at the same time. They have to, there's only space for one up and one down. And so this is not a super practical question, right? But the question is, if you know that that's true, one spin up and one spin down, but you don't know which one is which, and you take one of them without knowing which one it is, and you take it way over there, past where, they could somehow affect each other.
Right.
And you assume these spins don't change over time, which is not exactly true. And then you look at one, you instantly know the other one.
What do you mean by that?
Because they were originally one up, one down. And so if you look over here and you've got the up one over here, you know the down is still way over there. Instantly, without having to wait for the light travel time for that to happen. And so there's this faster than light communication, that kind of thing. No. Sadly, no. Because it's super not practical. Like, how are you going to take one electron and make sure that it never has any interactions and its spin never changes. Because once you take it out of that system, all kinds of things can happen, right? So it's not, like, it's a great thought experiment, but it's not a thing we're actually doing. Definitely, if you have a system where you know you're constrained in the beginning, and you look at the behavior of one side of it, you know what the other side has to be. But it's that probability distribution thing. It's not that the particles are talking to each other.
Yeah, it's just that you're predicting, like you're saying that because this is like this, this should be like this.
Yeah, exactly. Yeah.
Oh, okay.
But it was always true. There's the thing.
Oh, okay.
And again, this is a difference of interpretation. There are some people who will say, well, that's because it was always true. And you just didn't know until now. And there are some people who will say, well, looking at the one makes the other one real.
Wow. Like when, like, these things just like make me go crazy because
quantum mechanics is so great because it is absolutely true. Like, electrons really are, photons really are like this, but it's so weird. Yeah, it's great.
Wow. Yeah, it was great having you here. Thank you for being on the podcast.
Oh, thank you so much for.
Would you like to say something at the end or sum it up?
Wow, space is great. Everybody study astronomy. Astronomy is the best. I really like the attitude that you guys have of just wanting to learn as much as you can. I think it's such a fun way to look at the world, and I just want to encourage you to go talk to everybody. And as uni students, you have such a perfect opportunity to meet so many people who know so many different things.
True.
And your fellow students who are interested in so many different things are such a wonderful, like, this is such a good time of life to meet those people and to get excited about things you didn't even know existed before. And so I'm so glad you're doing this.
Thank you.
The thing that I would say is that we should not, those of us who aren't uni students anymore, should not let that hold us back. Right? We should also be out there talking and getting excited about things and finding new stuff that we didn't even know we should be excited about. Yes.
But yeah, I would really like to thank you, arranging this thing, inviting me for the
remote observing room. Yeah.
Thank you very much.
Well, you're very welcome. Thanks for coming.
Thank you.
This was the end to a very special episode with Professor Sarah Martell. Hope this episode helped you change your perspective about the universe and about our place in the universe. Thank you for watching. See you in the next one.